continue with our April 2025 online lessons. So we'll explore Hess law, which we touched on briefly in a previous video. We also looked at Hess law when we were talking about Born-Haber cycles. Hess law says that the total energy change for a reaction is independent of the route taken. Kana uchita physics, you know the concept of displacement versus distance. For example, you can there's always that straight line path from point A to B. It's always the same whether watenderera waenda neuko watenderera waenda na path B, watenderera waenda na path A. It doesn't matter. The displacement is the same when we look at 2 points. Chemistry tina Hess law anotaura chero kuenda neuko. When you go use either route, you get to the same point, same energy change. So it's independent of the route taken. At the end of the day, we must have a similar energy change no matter taenda kupi, taenda which through which path. So this is interesting. So let's talk about Hess cycles. These are the smaller versions of the Born-Haber cycle. A Born-Haber cycle is much bigger with more steps. My Hess cycles are smaller. So if you're given formation data, you can you draw a formation cycle. So let's look at the two situations where you use our Hess cycle diagrams. So we looked at the meaning of the enthalpy change of formation earlier on. So if you've forgotten this, you might want to go back to the previous video. So here you're given enthalpies of formation for, I see methanol there, carbon dioxide and water, and you can see all of them are exothermic. So if we give you this data, you can draw a Hess cycle diagram with this form. So we can ask you to use this data to calculate the enthalpy change of a reaction, and typically these reactions are the reactions that we cannot determine their enthalpy changes experimentally. We can't use direct experimental data to figure out the enthalpy change of these reactions. So we resort to these Hess cycle diagrams in the same manner that we used our Born-Haber cycles to determine lattice enthalpy. Here we can determine the enthalpy change of any reaction which we cannot measure experimentally. So this is the structure of the Hess cycle diagram if you're given formation enthalpies. So you have your reactants here and your products here. So this would be the reaction that you're interested in figuring out its enthalpy change. But now what you do is you can link this with this data that you're given on this table. So if I think of the constituent elements for the reactants, I can ask myself which elements form the reactant. So I put them here. And I can ask myself which elements form the products. So I can put them here. And then I can now say from these elements to these reactants, if I change these elements into these reactants here, that would be my enthalpy change of formation. If I change these elements into products here, that would be my enthalpy change of formation for the product. So I now have a triangle here which is linking the reactants, the products, and the elements that are the constituent elements for the products and reactants. So that is its structure if you're given enthalpy changes of formation. So let's look at a specific example and see this at play. Okay, so calculate the enthalpy change of combustion of methanol burning completely into oxygen to make carbon dioxide and water. Of course, this one is an example of a reaction that you can figure out experimentally, but you can also resort to Hess cycle diagrams to see whether this is to just calculate quickly how much energy is going to be produced. So you're given the enthalpies of formation for methanol, carbon dioxide, and water. So we have to create, this is the equation that we are interested in. It has to be balanced. So our methanol plus water, 1.5 moles of oxygen here give us 1 mole carbon dioxide and 2 moles of water. So we now need to think of the constituent elements for this and this, this and this, and we write them there. So we see that for you to form methanol, you need carbon, oxygen, and hydrogen, right? And the morality here is important. You can see that everything has to be balanced here. Okay, so this is important to have a balanced equation there. And we can also see that so what we have to do here is now plug in our enthalpy change of formation for the methanol. 1 mole of methanol you require, according to this table here, is you're going to produce negative 234 kilojoules per mole, right? Let's now link okay, before we do that, what would be the enthalpy change of formation of the oxygen? So oxygen is already in its standard state, so you are not really forming any oxygen here. So our enthalpy change of formation for the oxygen is going to be 0, because we already have oxygen here as in this side here as a reactant, and this side is going to be a product. So we were supposed to put an arrow pointing from here to here. However, that is not necessary because the oxygen is already in its standard state, so we are not really forming any oxygen here. So the enthalpy change for oxygen here, we are not interested in that. It's 0. Then let's link the constituent elements to the to the product. So we are forming carbon dioxide and water, and this is where this stoichiometry really is applying here, because here we see 2 O2. We have a total of 4 oxygens. This would be the O2 here and 2 times O here, and we also have this side 1 carbon, and we have 4 hydrogens, 2 there and 2 there. So the stoichiometry here was really for this side. This way there's a 2 here and a 2 here. Okay, that being said, the enthalpy change of formation for the carbon dioxide is negative 394 according to this table. The enthalpy change of formation of water is negative 286. However, according to this equation here, our main equation here, we are forming 2 moles of water, and therefore we are going to say 2 times our negative 286. So the total this side is going to be this plus this, which is negative 966, and the total this side is going to be negative 234 plus our 0 there, negative 234. So what we have to do now, what we want to do is calculate this energy change here for this reaction. So what we have to do is so that's the enthalpy change that we're interested in, the enthalpy change of combustion. Okay, so we need to think of how we get to these products. So we get to this product via this arrow here, which is the reaction that we're interested in, the enthalpy change of combustion. Or we can get to the products via route A, then route B. But for us to pass via route A, we need to go against this arrow. In other words, we have to reverse this arrow and get to this. Remember Hess law, the enthalpy change is going to be the same regardless of the route taken. So this is the route, the main route that we're interested in, and the other possible route is going via A through B. So for A, we have to reverse this arrow and hence reverse this sign. So when we add A plus B, this should be equal to this energy change. Or if you want to be specific, it's minus A plus B, because we have to reverse this sign. So minus this energy change here, that's a plus this energy change here, negative 966. This is going to give us the overall energy change. Okay, so that's the idea. We are equating the energy change that we're interested here in to this possibility of going through these routes. So this plus this should be equal to this. Okay, So let's create that equation. So enthalpy change of combustion is going to be plus 234 here, because we are reversing this sign, and hence